I'm going to stop my video because I'm not sure about the bandwidth where I am right now. I will be talking today from this reference. If you don't know about this book, I strongly recommend it. Deep Learning with Python 2nd edition. You can read this book for free online. I'll send the link, and I'll put the link in the chat window. And this is a very good book by one of the pioneers in the field. And, so I'm going to talk more about the concept rather than the implementation of machine learning algorithms for NLP. And so I'll go back to the book here. And so he talks about this NLP in chapter 6. And as you know, in deep learning or any kind of machine learning is basically a function that converts inputs to outputs. And, there's several stages in the design of deep learning. One is creating inputs from your data. Of course, neural nets must have numerical input. Typically have some kind of vector input. So the idea of how you change text into vectors, it's called vectorization. So that's really one of the important aspects of natural language processing. And the other is which neural networks you actually use. And I'll talk about that a little bit. So here you can see there are many applications, of course, that I'm sure you've been talking about those already. The application I'm most familiar with is this one. First story detection in Twitter. We just published a book with several different articles, and this was one of the articles. The first story detection means you look at Twitter stories and you want to find the first occurrence of a story. Of course, in Twitter, what happens is your stories get repeated by other Twitters. So you may want to localize where the story first came from, so that you can verify the accuracy or something like that. So certainly, this is an application of natural language processing. Okay. Another important one, of course, is sentiment analysis. If you look at movie reviews and things like that. And I think that in Charlotte's book, he talks more about sentiment analysis. But the same techniques work for any kind of text processing. So let me just scroll down here. So here he talks about vectorizing. So as I said, you need numerical input for your neural network. So there are different ways you can do this. You can segment the text into words, so you can do a vector encoding of words. You can do a vector encoding of characters, or you can do a vector encoding of n-grams, which are parts of words. And there are different methods for all of these. So what you do is you break down the text into tokens, and then you vectorize each token. So your word will be, your input will be characterized as a sequence of vectors. And each vector is created by taking a token and creating a vector representation of tokens. So in this chapter, he gives some examples of how you can tokenize words. So for instance, here's your text that you want to analyze. You break it into tokens, in this case words, and here the tokens are encoded using vectors. So there are various ways to encode tokens in vectors, and I'll talk about that. Now, the previous speaker talked about TF-IDF, or inverse document frequency. Another way of doing the encoding is with n-grams or bag of words. So you look at not just a word, but the words around a word. So let me show you how you can use this kind of feature, this kind of structure to create vectors for words. So I'll go back to this other reference. If I look for continuous back words. So let's go down here. So you can use continuous backup words as a way for as a way of vectorizing your words. So what you do is you initially you'll take a sentence and you can convert this sentence into now you're converting the sentence into vectors in order to bring out the relationships between words. Then you will use this vector representation as an input in order to into a neural network that will create your vectorization. So you can you have skipgram and SIBO as two alternative ways of creating vector representations of words. So again, if you want to do either of these, you will encode your sentences. So you need a training set. So you have a training set of sentences, and by analyzing these sentences, you will be able to analyze find words that are closely related that often occur together. So in continuous backup words, what you do is you take your sentence and you have weights on each different word, and you look at neighboring words and you adjust the weight of the word in context based on the weights of the neighboring words. So that will give you a vector representation of words that resembles vector representations of words that it often occurs with. Now, if you use skipgram, it's quite similar, except you use a word, you look at the words in the context of the word, and you adjust the weights of the words in context based on the weight of the word. So in this case, you are using the weights from several words to adjust the weight of a single word. Here you're using the weight of a single word to adjust the weights of several words. So when you have smaller data sets, you probably want to use the second one. Because here, if you have a large data set, you won't be able to get very good weightings of individual words. But here you can have, if you have few words, you can get weightings of larger numbers of words. So that's one way of creating vector representations of words. Now, Charlotte, when he discusses this, he says that this is not a preferred method because it's too specific. Modern neural networks can take data without context and create representations. But this is still quite often used in the literature, both of these, skipgram and SIBO. Now, another way to encode words or characters is just use one-hot encoding. That means each character would take a single, for each character, you'd have a vector. So the dimension of your vector space would be the same as the number of characters. And each character is encoded by a vector that's 1 in one place and 0 in all the other places. Or for words, if you have a set of words, if you have 1,000 words, you can encode each word as a vector that's 1 in one place and 0 in 999 places. So this leads to very large vectors encodings for vectors. So here's a code where he does this. you just take your sentences and you locate each word and you create a new vector for each word. As I said, this will lead to very large sets of vectors, and it really does not encode relationships between words. If each word has its own specific vector, you can't tell from the encodings of different words whether these words are similar or not. So you can do one better than this. Well, all right. You can also do hashing to reduce the size of your vector, the size of your vector space. Instead of using vectors of length 1,000, you can hash your vectors into a smaller set of numbers, but then you may run into problems with collisions. Right, so here you have vectors of length 1,000, and they're hashed into a set of numbers of 1,000 numbers. But as I said, you may get collisions. You probably want to use a larger hashing space than 1,000. Now, word embeddings is a vectorization of words in a way that reflects the meaning of the word. And to do this, you do need to train your embedding, which is typically done with a neural network. One way of training your embedding is with the continuous bag of words or skipgram. So this is a nice representation of the difference between one-hot encoding and word embedding. In one-hot encoding, each one of these columns represents a word, and the black means there's a 0 entry, the white means there's a 1 entry. So this would be 4 words, 4 different words, with 4 different one-hot encodings. Now, word embedding would reduce the size of the vector, and here the vectors don't just have one non-zero entry, and they have floating point entries. And you can visibly see whether words resemble each other. For instance, these two vectors here, they look quite similar. You have somewhat similar pattern between the two. And that means that they'll reflect words of similar meaning. So you can pre-train your word embedding. And there are some very popular word embeddings. One is called Word2Vec, which you can download from the Common Machine Learning Library, and Chalik gives details on how to do that. Or you can create your own word embedding while you're solving the test that you're trying to solve using the data using your training data. So for instance, here you'd want a coding, say, if you have words accurate and exact, these two words have very similar meaning. And what will happen is that these words will have similar contexts. So when you do learn your word embedding, there will be words that you often see with accurate, and you often see the same words with exact. And that will reflect in creating similar vector representations for accurate. Here he says, the geometric relationship should reflect the semantic relationship. That's what it's saying. That's what I showed about. If the vectors look similar, they should represent words with similar meanings. So he gives an example here of word embedding space. This is quite idealized, but it gets the point across. Here you've got 2 dimensions here. Here you've got 1 dimension. So you can say this dimension varies from different species. So dog is over here, cat is over here. So dog and wolf are both kinds of dogs. This one is domestic, and this one is more wild. So you can see the same relationship between dog and wolf has a similar relationship with cat and tiger. You may keep a dog in your home, you won't keep a wolf in your home. You may keep a cat in your home, you won't keep a tiger in your home. So you can assign dimensions in your word embeddings to different aspects of the meaning. In this case, this dimension would correspond to the level of how wild the species is. And in this case, the dimension reflects the changing between species. Another example here he gives the relationship between female and queen is the same as the relationship between male and queen, king. Also, you can have a vector that reflects plural, whether the noun is plural or singular. So this type of wording embedding as I said, has some meaning encoded in the vectorization. And that means that the neural network is better able to use this information to derive conclusions. So here he says you may learn a new embedding space with each new task, but what you typically do is you take a pre-trained embedding and then you modify it. So this is like transfer learning. You have some network that's already trained, and you retrain it with new data. You can do something similar with word embeddings. You have some previous word embedding, and then you can modify it based on your particular task. So you'll start with a corpus of words, maybe 10,000 words. And then each one of those words, you will feed through an embedding layer that will change it into a vector. And then you use your vector in your actual neural network when you're trying to interpret your text. All right, so here he gives an example of, if you look at movie review, first you prepare the data, you look at so you can't possibly do all words, especially in the small data set. So you look at the most common words, and then here it's only looking at the first 20 words of the review. Well, hopefully that will be enough to tell whether the review is positive or negative. Here he has 8-dimensional embedding. So you can see that this is much less than one hot encoding. One hot encoding would have a 10,000 dimensional vector. So we'll turn the word sequence into embedded sequence because each word will become a vector. So that's another dimension. And then you'll use that as your input to the neural network that actually does the classification. So if you've read through code before, this is very common type of code. Of course, you set your training and testing sets, and he gives some explanations here about how to do that. So you can actually copy this code and run it and see how it works. All of this data is available online. So here, as I referred to before, you can use pre-trained word embedding, and you can either fix those or you can adjust them as you do your task. Now, once you have your word embedding, so here he actually goes through the example step by step. It's another common embedding, the glove embedding, word embeddings. I already mentioned words of act. This is another one that was created recently. Let's go down. And here it's not performing very well. You can see the loss is quite high, but that's because he's working with a very small data set. Another reason why it's not working well is he's using a very simple neural network. After he has his word embeddings, he's using a very simple neural network to analyze the data. And what he says later on is that it's better to use different structure of neural network, like recurrent neural network or LSTM. The reason is that you don't just want to look at words in isolation. There's relationship across words. So you need some kind of memory. There may be a word later on in the review that affects the meaning of the earlier word. One of the examples people often give is the word not. For instance, you can, if you say this movie is by far, or this movie is really the best movie I have ever seen. But if you also said, I would not say this movie is the best that I have ever seen. Now you can see that those two sentences mean something quite different. If I say this movie is the best I've ever seen, and if you say, I would not say this is the best movie I've ever seen. So you need to remember that word not. You can't just look at words in their immediate context. So you need some kind of neural network that will have some memory. So here's where he finishes talking about word embeddings. And then here he talks about that you need some memory. So one way of doing that is with recurrent neural networks, and another way of doing it is with LSTM. Or you can use convolutional also. Recurrent or convolutional or LSTM. Actually, he says recurrent does not work very well because the memory is too short term. Because you may have some words from very early on in the sentence that affect words very late on in the sentence. And with recurrent neural networks, the memory diminishes as you go along. There's kind of a fading of memory as you go along. You may want some long-term memory. So instead of recurrent, you may want to use LSTM. All right. Well, that's a very top-level introduction. I suppose if you want to go further, I do strongly recommend this book, which does not just do the natural language processing, but is really an introduction on all aspects of machine learning, of deep learning, especially deep learning. So you can see the table of contents here. And there's code that goes with it. There's downloadable code that you can execute. In fact, if you've ever used the Keras tutorial online from Google, it's based on this book. All right, so I think I'll stop here. And if there are any questions, I'd be happy to try to answer.